Great. So as I go through this, I'll go through a portion of it and then ask questions, and then hopefully you guys can give me the feedback in terms of the system. Going back here, good second. Okay. So I'm sure some of you have gone through this. Today's system will be FPD Link 3. It's a camera system that's used for automotive, but it can be used for anything that's automation. Automation could be warehouse. It could be devices that are moving in a warehouse, could be devices that are on a Pepsi or Coca-Cola product line. It is that good of a product that it can sense short range and long range. I would say about 50 or so meters, and depending on the lens here, it can even go longer. So what does a camera compose of? There's the lens here, there's an imager board, and there's a connection between the imager board and the serializer. The serializer takes the data from the imager, from the sensor and the optical system. It transmits it over a protocol, MIPI protocol, CSI2, I2C, and then it transfers it. Every pin here is called out for a specific reason, hardware-wise. It comes to the serializer. Serializer processes it, sends it over the link here, which is about 15 meters with 4 interconnects. Now I give you an idea here. Let's say your imager is too high of a definition, too high of a optical link in terms of identifying objects. You have to go up in terms of data, in terms of matching this with that imager. So you could have a very high resolution imager here, and the serializer needs to match with it, because the imager could be sending data over 10 gigabits, and the serializer could be only processing at least this family up to 5. So we need to go to the next family higher. Okay, this is the data out over the link. This is a cable, and this is the data in. If you look at recent cars, if you put the car in reverse, recent models, maybe 2018, 2019 for sure, 2020, and moving forward, they all have a rear view camera. And that rear view camera, this is placed in the back of the vehicle, and this is placed at the head unit. And this is the deserializer, and this just decompresses the data, deserializes. So here they have 2 families depending on the speed. And again, they use this protocol, the MIPI CSI2, I2C, high-speed GPIO. Does anyone know what this GPIO means? High-speed GPIO? Can take a wild guess too. Okay, so this is the general purpose input-output. This is data pin 3, data pin 4, data. And why this is so critical, when you go back to the, and I'm going to fast forward a little bit here. So you have to know the registers of each protocol, right? This is the 953. And each protocol has an address of those, the data in, data out pin. It has an address, a register address here. So each of these addresses have to be adjusted for or accounted for. And then when you look at it software-wise, the same thing. It's going to come up in a second. Again, here, more in depth, each protocol, and then here you have values in terms of the RF values, and yep, right here. So this script is for the IST. This script is for the sensor. This is just purely the sensor board. And that's why it's critical to, as you can see here, set GPIO2, set and GPIO3 to outputs. To set that, you know, and maybe this is for the software engineers. This is for the hex values, and here we're giving the code, and in here we're pretty much putting a note. This is what I'm doing, and this is very critical for software engineers, is to put the notes there in case you come back. Oh, okay, what is this address? It's obviously on the serializer end, right? And it has an address, a location, could be an alias or device for ID, depending on if run locally or remote. What language you think this is in, or if you know that? Any guess here?
C++.
That's a good guess. Anybody else?
Is it Python?
Yes, it's Python. And why it's Python, Ahmed? I mean, you can look at the coding structure, or you can look at something, just one line, and if you can see it, point it out.
At the top of the script, it says .py, so that was my guess, Python.
Yes, good. So good catch, Mushtaba, and good feedback, Ahmed. So it's Python. It could be, Ahmed could, you know, he probably wrote a lot of code here, so he can see it by the way the structure is of the code is written, and then you can look at it here. This is a note: sensor power on and reset .python. So this whole code is written for which part of the system? The sensor side, right?
The sensor, yeah.
Yep. So why I say this is critical, I mean, the software engineer, every aspect of the system is critical. Why? Because if he set the input as output and he set the output as an input, guess what's going to happen? As we go back here to ST here, right? We're going to have issues, right? One side on the other. And then also consider all these pinouts. This is mechanical. This is part of the hardware / mechanical, ensuring all the pins are to the right location, right? The pinouts, the stack up. So as you have the stack up, you want to make sure these are all aligned. If one of the pins is not given power, this whole device will not work. From the image sensor to the display, to the ISP. And the same thing with the code. I would say the same thing. You could have one one reverse line of the data out to the data in, and then you have that potential issue where you have to start debugging, or is the issue here or is the issue there? Or it could be that the way that the structure is done hardware-wise in terms of laying out the PCB. And the software engineer thinks that, okay, I have an issue with my code, and they could go out there and rewrite their whole code for 3 days when it's a data continuity issue. So let me know if you have any questions here in terms of just the basic background about it. Okay, great. Then we'll move on to, so the basic design rules confirm hardware configuration. And what that means is, that means the sensor you've selected works with the serializer. Because if the sensor is too high of a resolution, the serializer cannot keep up with it and cannot transmit the data. So the first thing, confirm your hardware, confirm your MO. Go ahead, Mo.
Sorry, I have a question. I lost you guys for a second, but I was gonna say, so when you say a sensor, right, do you mean the camera? Or not?
So good question. I'll bring it up here. IMX 290, IMX 390. So as we're going through this, we can go back one step. So the sensor here is, you can get it from many companies. I tend to like Sony, Onsemi, and others. So this is the lens right here. This is at least one of them here. Where's the front view? Nope, I don't see a front view. Let me look at, okay, this one is good. So this is the lens here. And then if you were to look into it, this is the optical link below it. So you got the lens right here. Whatever it's detecting, it goes into this board, processes it, sends it over a connector or a link over to the serializer. And there's many different types, depending on what you want to achieve. If it's a warehouse application, if it's a Pepsi line, if it's a front camera in the vehicle, it's obviously gonna require a much better resolution at a higher speed, right? Would you say the front camera or the rear camera of a vehicle requires a much higher resolution and a much higher speed? Okay, I would say the front camera, because you're going at 70 or 80 miles per hour and it needs to detect objects. Versus the rear camera, you know, even if you're going really fast, 5, 8, 10 miles per hour. So that's pretty much just giving you the object behind the vehicle versus in front of the vehicle. It's detecting something. It could be a pothole or it could be an object on the road, and then alerts the driver. In terms of the Pepsi line, you can use this on a Coca-Cola factory line. It needs to identify that every bottle has a sticker on it. and that could be 10,000 per hour, 10,000 bottles going by it in an hour. So in selecting the imager, you have to know the application you're behind, right? Or it could be a warehouse. It's just scanning boxes. And if it's scanning boxes at a distance, you need to pretty much know your end application to select this image sensor. And the higher, I put here IMX, this can go higher and higher. They probably have a 690 and others that are coming on board. Imagers. So right there, you see a front view application, and depending on what your end application is, you want to select that imager for it. And once you select that imager for it, then you continue onward. Then your serializer has to, this is the control board that's taking the data from the imager and it's processing it. You have to match it with this imager. You cannot have a slower one, or you can have a faster one, but you're going to be paying for it without getting the data. And then so forth. Here, confirm the IDX pins. So that means all of your configurations right here, hardware-wise and mechanically and software-wise, this is very critical. Identifying each pin and what that pin is and its responsibility, and then local read devices also, again, going to the Python, identifying each address as it reads from the 953 to the 954, 960. This is very critical. Sometimes I would say the program here was written in Python, but it could be assembly, could be C, C++. And Java would be here. Java would be here. So you could literally have 2 or 3 languages here. You could have one programming language here, could be C or C++. Here's Python, and here's Java. Most of the time when it's displaying an image, it's Java.
Sorry to cut you off. Quick question on that. So is there a difference in terms of the process, the speed of the process, if you have Python embedded or versus C or C++? I know Python is a high level, compared to other programming languages. Can you have an insight on this?
Good question. I would say for the software engineers or computer science engineers that are on the line, I know from what I've seen in the past, Java is used, it's good for displaying here. But the rest of it, if you were to write a code between the full HD image sensor, serializer to deserializer, for the computer science engineers, which language you see it as easier, simple, and not heavy data driven, where you don't have to write a lot of code, where it takes time to process and it takes time to process the data. So I know there's a couple of software engineers, note it out, like let me know or tell me what you think as computer science engineers, and then I will give you my feedback. Or Okay. From my view, it's all about the communication. So if you have Python here, what do you think? You have to have Python here or another language?
It should be
it makes
Python.
sense.
Same.
Python. Sorry, yeah, go ahead.
Oh, I was just thinking you have the same language.
Exactly. Okay, good. What do you think if here you had Python and you go into the image processor? Now you're taking data and then you're turning it into an image.
I would say here using a different language, much faster, lower level would be faster.
Yep, exactly,
Wrong.
exactly. Yep, exactly. So back to your question, Mo, and it all depends. Like you can also like look at it as the micro will accept or the processor will accept one language and it will process it faster versus another. But you almost have to look at them independently. This is block 1, block 2 and 3. They are talking to each other. It's like the right hand, left hand. Here, it's a different person. This is on the outside displaying. This is capturing an image. So each one, sometimes you could use the same language for all of them. In some instances, you have to differentiate between them. So going back here, looking at the addresses, this is a must for like software engineers. You have to match these up. You have to match them up in terms of every address, every code, and I'll go back to the code in 1 second here.
So
if we're
in the
looking,
meantime, while you're doing this, plus, so I would say, I don't know, correct me if I'm wrong, from prototyping the point of view, it's really excellent thing to do where to program the first couple blocks using Python versus using a different language, and the last block, which is the image processor, maybe different language.
yep, exactly. So here, I'll let you guys take, I'll let you guys take a guess of what's happening here. Maybe make it smaller so you can see the second page. So what's happening here in terms of the code? This is the sensor board taking the script for it. And this is good. I mean, they are laying it all out, like setting up the variables, setting up GPIO 2 and 3, setting up GPIO 2 and 3 to high, to outputs. So these are very critical. As you can see, these addresses, right? This address right here, this address right here, this address right here. And it's very critical to set these addresses up, because if you set one of them up to an output, let's say I set this up to the input here, then my board will not function. So just going back here. So from a software perspective, is this clear, or do you want more in depth about it? Local read on both sides, from the imager board to the serializer, and then over the link, and then to the deserializer. Ensure that you match all of your addresses, right? Because if one address is not matched with the other, then you're thinking, okay, I have an issue when it's actually the input and with the output. And the same thing, the pinout, right? The pinout configuration is critical. Whether you're looking at it from this side and that side, you ensure that you match all of these pins up. And then we go to the next one, validate the serializer ID and the deserializer, and then confirm the I2C pass-through settings, both for the 953, 954. You got, again, we're looking at addresses, right? To ensure that these are matched mechanically, electrically, and software. That's why the system is so critical. It has all of these aspects, right? It has all of these aspects, the mechanical portion, the hardware portion, and the software portion of it. And this camera could be used, not this very one, but you could have laser and biomedical engineering. You could have lasers treating specific cells in the human, and it identifies those cells. Here we're talking about automotive and factory. Even in a drone, you can use this type of system, and medical too. The sensor or laser identifies a particular cell. It goes through a software loop. It identifies it, and then it could potentially treat it also. It's the same basic design rules, where you have the mechanical setup, and then here confirm your lock state on the 954. Again, we're going back to the addresses all the way from start to the end, looking for errors on both. The 953 is receiving the data from the imager. The 954 is sending it on to the display. If there are any errors, consult with serializer and the deserializer link. So if there are errors, what do you think is going to happen? So a data packet got here, it's corrupt. What's going to happen? Is it going to stop if you were writing a software code? Or if you're designing the hardware, what do you think is going to happen? You want it to stop, or you want it to do what?
At least to stop, because if it's going to get something wrong, then you would get the wrong feedback, and your response is going to be wrong as well. That's my guess.
That's good feedback. Anybody else from the software guys? What do you would want it to do? You want it to trigger what? So if you didn't get a good data packet, you're gonna have a loop back. You're gonna say, okay, I didn't get a good data, a while statement or a if statement. If I got a corrupt data packet, then go back where? Restart. Send the data packet again. Request the data packet. Because if you're going in a high-speed car or high-speed train or a drone, do you want it to get that data packet? Of course, when the device comes back, you're gonna look through your data packets and you're gonna say, "Oh, I got an error here. Why? Did something happen to the device? Was it an intermittent connection?" But in the software, you want it to rebroadcast. If statement or a while statement, while loop, it's gonna come back and it's gonna say, "Okay, I need an image again. I got a corrupt image, but I need to get another one." So when it requests it again, the hardware should be set up as such, and the software, it's asking again for the image. So if you got an error here, consult with serializer, deserializer link, meaning come back to them again and request it again. Initialize camera, back to the channel. If not, consult with serializer. So if the image is not being broadcasted here at the 954, which is receiving the image here, it's going to consult back here. It's going to say, hey, I didn't get an image from you. Come back and give me the image and then go back. This consult means like a if and a while statement. Like if this is going to happen, I need to go back to step 1, or I need to go back to step 2 or step 3. So as you're writing this software program, keep in mind this, and even mechanically when you're designing, keep in mind all of these. This is a good setup, and I would say apply this flow diagram in everything you do, whether it's hardware design or mechanical design. It doesn't have to be in this structure, but it needs to have a flow to it. If this happened, if I did the stack up, great. If I didn't, I go back and I ensure that I got my stack up corrected. Because it could be here a stack up issue, where with vibration you have an intermittent connection and it's not given to the serializer, the image. If we have done the stack up, then we go to code. If we did the code, then we go to the environment. Then we go through a checklist and ensure that what we have here is operating properly. And then here, reading off of the CIS output, CISI here, output, the output of it going right to the imager. And then here we display it, we read the data. Any questions here on this flow chart? Okay, great. This is electrically looking at it. You want to have the right voltage setting. You want to have the right target. You don't want to, by having a voltage inrush or current, you could potentially blow one of these components, and then have the right settings, the minimum, the max, the voltage range, and the target, suggested resistors, and then assigned addresses. Back to the software here, you want to make sure that you have all of these lined up also, and then hardware wise and mechanical wise, you want to make sure these are fully functional, because all it takes is one pin. It takes one pin not to work and the whole system doesn't function, right? Or one address setting or one value is too high or too low for the voltage or for the stack up in terms of mechanically and in terms of software wise. Voltage range. Here we go more in depth. So in terms of here, take a wild guess, or if you know, let me know what do you think this is, the 60 FPS.
Frame per second. This is 60 frames per second.
Yes. Yep. So at 60 frames per second, this is good at identifying some objects, but knowing your end application, if it's medical and you have to find a cell, I don't think 60 frames per second will work. But if it's a Pepsi line, this could be great, because per second, it can measure the label and say, yep, this is good, go on. For rear view camera, maybe this is too much, right? So per second, it's like it's identifying that many frames as an imager. And then here, you're looking at the serializer where you have now the power, and then you have the clock, and then the clock out, and then internal settings, and then this is the bidirectional channel where you have here. I'll go back to this point to note to you here Does anybody, or let me know if you know what STP means? So the transmission between the serializer and the deserializer can happen over coax, which is a single conductor, or it can happen over shielded twisted pair. Different type of cable. With a different type of cable, you're using different connectors. And if you're using different connectors, it also affects your hardware and your software. For coax, I'll pull it up in 1 second. This is good. So for coax, you have one connection here, and that connection takes the data to the serializer and back and forth. It's a bidirectional channel. For shielded twisted pair, HSD connector. For shielded twisted pair, you're looking at multiple contact points. You got 4 connections versus coax, you have 1 connection. So coax simpler. HSD is just the data for it. You have to ensure that you have the right setup. And when I say the right setup, you got four pins here, and then you have 4 pins here. 2 are for data, 2 are for power and return. And software-wise, you have to set it up as such, and hardware-wise. Deserializer, and then you have your power here, and then you have your imager board, and then here you have also the reference clock. F0, F1. And then here, just some synchronization mode setups where you have the reference clock in and out. And the same thing here. Non-synchronization, so if you're configured one way, ensure that you keep that and you stay with it. Here is to do some a little bit of electrical, and also consider the software side of it. In the back channel bit rate, this is how it's factored. Let me know if you know what. So this is bidirectional, and this is 2 times what? What do you think this M is? If the end speed is 50 megabits per second, what do you think this 25 is? 25 M.
Megabit per second as well.
Yep, exactly. So you're looking at the bidirectional channel rate 2 times. This is for your clock and measuring your clock speed in terms of frequency, and the same thing here. So if you had a value of 20 here, you would have an issue, or if you have a value here of 60, you would have an issue. So the forward channel and the data bit rate, also you have to ensure that you match that. This is the forward channel, this is the back channel. CSI, throughput, and then this is per lane, 800 megabits. So ensuring that you have all the data matched up. Obviously, this is the higher data rate here. Where you think this is going? This is coming from. This is going to the sensor or from the sensor? The forward channel bitrate.
So I think this is out of the sensor towards the sterilizer.
Yes, exactly. So as you move forward, this is making the request here. This is giving the request, and then the same thing. This is the throughput, and this is the per lane. And then here it's pretty much the link. It's giving you the budget for it. The F1, F0, F1, F2, F3. Hardware-wise, electrical engineers, a little bit of the software, you have to ensure that these are synchronized. Because matching them up with the F0 times 25 megabits per second, it's not going to give you the right output, right? Here, the clock out, it's not going to give it to you. It's going to throw the value out, and it's going to throw the speed of which the frames are captured and they are sent out. And the same thing here in terms of the mode clock setting. And here we're going through addresses, like software-wise, identify all of the addresses and how much speed they're taken, how much speed they have coming out of them. Okay. And here it gets more detailed. So in terms of the 953 illustration of the 2-port, you have the data coming in. And then here, what's happening here is inside a processor. But knowing your input, you should be able to calculate your output, right? Knowing your input here, you should be able to calculate your output. In case, why you want to do that, in case you have an issue, then you say, okay, is it software, is it hardware? Well, if you can measure here, tap into this, hardware-wise, you want to have a VIA. Does anybody know what a VIA is? Okay. If you don't, no issue. VIA PCB design. So with that board, with this board, it's going to have many layers. So what it means by layers is going to have the top layer, where you see everything here, right? And it's going to have a layer in between here, layer 1, layer 2, and it could be all the way up to 7, right? So the VIA here, having a VIA, you're able to take, if you have a scope, you would tap into the VIA right here, and then look at the output, measure between them, right? So the design board with it you're making, or that we would be making, we wouldn't go with the first design board and take it to production. We would have these VIAs there. And why would we have these VIAs here? Have a VIA here, and others where we have inputs and output.
So I need to check the error at each point through the layers, so you know where exactly you have something wrong.
Exactly. I mean, you said it. if we have an error. But if we don't have an error, that's good. But if we had the right input and we have something here doesn't look right with the clock, right? Then we can go back and measure and say the value between here and the input should be this much. Is it a decoder problem? Is it a deserializer problem? Which one is it? And then we're able to figure it out. Or is it a software? Or is it, if we have too high of an input, then we need to look back further this way on our design. But if it's here, if it's coming into the port, and then we got an issue on the output, then we need to definitely look and check between them. And the only way to check between them is to, as a design hardware engineer, you need to consider these vias. Put them in first. So there's a via that connects, like this trace is going between, it's going right to the source. And there's a via that here, it doesn't interfere with the rest of the traces, right? So there's a via, you want to set it up in a way where it's not shorting the rest of the circuits. It's in a way that you can tap here, look at it. Okay, I got the right value. I got the right voltage, right resistance. Okay, my issue isn't here. My issue could be with my output from here. Any questions? I know most, if not all of you, and even when I was a few years back, I didn't know what a VIA is, but I found out that it helps in the design stage. So as you're designing, you don't want to design your end product like this. This is good design, but if you had an issue between this processor here and the output here, you can't really diagnose it. You cannot really troubleshoot it, right? You need a couple of vias. You need a via here, and you need a via here to know that the signal that got in is right, the signal that got out here. And if it's right, then before you go to production, you eliminate the via. And there's many of them. There's this setup here where it goes through the whole board. There's one that goes to the, looks like just the first layer, and there's one that goes in between. So there's many different designs for the via. Any questions here? Okay, good. Here for the communication, I²C, using various pass-through settings. Again, hardware-wise and software-wise, ensure that it's matched. Addresses are very important. Here, they start calling them out. RX, interrupt, debug, right? So if you're software-wise looking at this address, and if we wanted to do debug, this is very critical to have this address and the setting for this address to be the right setting with the serializer. Okay, we go on to the next one. Check errors also. Register used doing diagnostics, right? So within this processor, you have registers that are set for error count. They're set for doing diagnostics and so if the length of the cable is too long, you will have this. So let's say this address came up on the 953, this address came up. What do you think is the issue?
So it seems to be we have two things here to look at. We have the line length mismatch, and we have counts number. as well. Oh no, that's the only one which is the link. That was 5C.
Good.
Different
So,
code, yeah.
and the 953, if you had an error that came up and that got displayed with this address, software, you're setting it up, hardware, you connected right, and then you have this address, okay, I got this issue. So very important to know when you get the error, what does that mean? And then you go back and then you check for the settings. Serializer, deserializer link, specifically the two links, flow diagram, flow chart for it, have the right settings for the general purpose input output, for the back channel, forward channel, and to have the right settings for all of them. Okay. So this is the hex address, and then you have all of, for this specific address, you have this many settings. In each setting, bidirectional, forward, I squared C pass through, looking at the transmission, and each one is one setting, setting 1, setting 2, setting 3, and looking at the bits. And here it goes back. If you recall earlier, we talked about this 25 megabits per second, right, in terms of the clock speed, and then 50 megabits per second. Compatible, right? Going back to 2 times this, and then you're getting the 50 at the 110, at the 101, and at the 111. BIST procedure, just going through the 953 serializer and deserializer settings, going through them. Again, this is for this specific camera, but any design that you're doing, do this upfront, do this early on, right? You would save yourself a whole lot of time and effort and development, setting up the device ID, setting up the device status. Again, enable or read off of this or write into the deserializer, decompressing the data and then send it on to the display board. Here you have specific addresses for the multi-channel. Here you're going through it, flowchart for initializing the image sensor using the GPIO. So as you're getting the image from the 953 to the 954 and then setting it up for the camera. Here, you're looking at the back channel, the forward channel. Forward channel is always going to be higher in speed. The back channel makes the request. The forward channel sends the request. And then it processes it. In this specific example, it's just talking about the functionality of the camera and displaying the image. As we set up a program or set up the software, we can make this imager here identify certain objects, right? Identify object 0.1 meter or 10 millimeters in height to 1 meter in height or width. And then it eventually, if you write enough of programs, it can start identifying many objects. When it identifies those objects, then here you can send it to a display or you can send it to an ECU. So if this was forward-facing camera, identified a cat or a dog or a person or a kid or a bike in front of the car, driver is not paying attention, this imager gets displayed throughout the system, goes to the braking ECU. The braking ECU could be communicating in multiple protocols or languages from the braking ECU to the brake. That's probably CAN. This is happening at 35 picoseconds. From the imager to here, and from here to the ECU to the brake, this is in a fraction of a second. I haven't calculated, but I can tell you right here, as this ends, this is at 35 picoseconds. With our human eyes, we cannot measure 35 picoseconds. So it's acting much faster. Think about this as if you were a farmer and you had, you don't want to go out there with a tractor and spend 10 hours to find weeds. You can send this on a drone at 35 meters or 20 meters. It can identify the weeds in the farm, 700, 800 acre farm. And then by identifying the weeds, you're sending this image to a nozzle. The nozzle will spray based on your identification of the weeds. You treat it, the nozzle opens for 5 seconds or 3 seconds, depending on the image that you've identified or that you've captured. It treats it, done. So this is in a drone application. This could be in a car. This could be in a Pepsi line. Identified something, it triggered it. Let's say they were like bad 10 bottles in a row. It stops the line. It should stop the line. If there's an issue with the one label, okay, then it puts that aside. You should make a statement here that goes back to a motor controller that's bringing the Pepsi bottles in front of this camera, and it goes back to that motor and it says, you have, or stop, cut power, or disconnect, right? It goes, here we talked about the car, the ECU, the drone in terms of treating weeds in the farm. And here you can look at it as a Pepsi line. What's making the bottles come over? It could be a motor. And go into the motor ECU, cut off power, stop the line, shut down, because now you should have an if statement or something here, a while loop here. If you have so many bottles in a row, Pepsi or Coca-Cola, that have a defect on the label, you can't fill up the diagnostics line or the relabel. There's something happening beforehand. You send within your software, you have to note this to send this signal, and then to send the signal onward to say, hey, cut off power to the rest of the bottles that are coming, stop the manufacturing. Any questions here of how you can use such system? Or better yet, where you think you can use the system outside of the items that I noted, farming, agriculture, or cars, or a Pepsi line? And everybody has to pitch in now. And I'll start with Hassan. Where do you think you can use it, use this camera system besides the three that I noted?
I think it can be used in many production lines where you have defects. Yeah, this is in general. Wherever you have a piece that has defect and can be recognized, and you should stop the line. Either you remove this component or part, and then you continue.
Okay, great. Ahmed, I'll give you a clue before you answer. How about like you know, where we get our copper. And when I say we get our copper or our coal, or let me know what other application you think it can be used in. Okay, we'll go on to Ali. Right, you can use this as security guard, right?
Oh, I didn't know I was muted. Yeah, I was thinking we can just use it in like everyday like regular buildings for security.
Yeah. Imagine you had a kindergartner walk into university, right? It should identify him right away, but if there's an adult within 3 meters of that kindergartner, and you can set a specific setting, you can have it as a security guard and say, well, you know, after 8, this door closes. Should we have somebody working there from 8 at night to the next day, 8 in the morning? Probably not. But if you had camera systems set up such as this, you can definitely have it there.
Yep.
Okay, the next person, Brahim.
Hello?
Yes, can hear you.
Yeah. So I guess you can use these camera systems sort of like scan things, I guess.
Yep, that too. You can use them for many scanning purposes, right? I mean, whether you're going into a facility and you have those bars that you already printed, and then you're matching them to a database, right?
Mm-hmm.
But the camera has to take whatever that label is on a person. Like, let's say you're going into University of Michigan, big house stadium, right? You got a lot of people. Then, you know, you got a device and it's checking people, and it can do it fast and it can do it accurately, right? You have a database built, and then you have a camera system that's checking every ticket or barcode that's on your phone, and it's checking that and saying, okay, yes, this ticket has not been used, and it's effective, right? You know, if you're doing 60 frames per second, you know, humans cannot go very fast in 1 second. You know, if they're checking their tickets to go into the stadium. Okay. Mauricio, up to you if you want to pitch in. As far as applications, if you...
Yep, I'm okay, boss. Listening in. Thank you for letting me join.
Sounds good. Mo, I know at Ford you guys got plenty of cameras, but any other applications outside of Ford or outside of automotive?
Hey, sorry guys, you can hear the wind. I'm outside. But yeah, I was gonna say, obviously you can use it in the automotive industry. This is a big deal. But yeah, I mean, like the folks were saying, it can be used in a security system. Obviously, all type of security systems, definitely, or object detectors. That's something to consider using this application. I'm not really at forward into this topic, Abbas, and this, for me, all what you said was brand new stuff to me.
Oh, yeah. I'll probably learn next week from you about Ken.
No problem. You're welcome.
Mustafa?
I was thinking more in the sports area. They already started applying this, but they use like a video assistant referee, to sense whether the ball, is past the line, and if it's a goal or if there's a handball. They started applying it like really recently, but I think that's a really good application because it gives the referees a different, like more eyes, kind of gives them more like a different kind of more help in a way, and it's more accurate. It gives you more accurate results and it's more fair towards the game. Oh, that's really outside of automotive, but I thought that would be a really good idea or a really good application.
Good. You hit it on nail. So I have to, as a TE sensor, and then I'm going to say soccer here. You know, when you set this, I have to show. So TE makes sensors here. And when the ball crosses, it senses it. And then, you know, it's on the side posts. So yeah, that's a perfect, you know, like it senses the ball has crossed and maybe somebody got the goalie got the ball out, right? But who is there to judge, right? The sensor is. And the sensor can tell the ball was all the way in, or it was halfway, or it was like 10% of it left. So TE does make these sensors in soccer, and they are very similar to this. Not the same, but very similar. And the last person. Hayam, what application you think this will, or that you can think about that you can apply in the real world?
I think the credit card sensor, because it's used widely.
Yes, I mean that you can. As we've seen in the pandemic, right? You know, you don't want to hand over your credit card, because if you hand it over and somebody's running it, you're exchanging, you know, whether it's the virus or germs or something else. Where here, you know, a special system protected, it can detect, and once it detects, then it's able to match that and say, okay, yes, RFID or other systems, but yes, that system too. So I'll give you an idea where our power plant DTE Trenton. So I used to work in this power plant, right? Yes, you can see this pile here. It's terrible, but that's the reality of it. I used to work in some of these power plants, but specifically this one. And the coal when it came in, coal, all of it is black, but east coal, west coal, low sulfur, high sulfur, expensive, cheap. We had to have the right mix or close. And when you have a good mix, it goes through, it burns, and then it emits, it emits emissions out there. But if you have too much coal with high sulfur, and the person that's mixing it is like Bob the Builder, like Homer Simpson and a bulldozer, right? He's mixing it. He cannot tell if he's mixing too much east or too much west. And by the time it gets to the stacks, and there's the EPA, Environmental Protection Agency, has emissions here, the power plant is already getting fined. They're already paying the price because they can't mix the right. But with the right camera, it can measure the shininess of the coal, right? And it can mix it. It can say, well, this one, I just put one dozer of east coal. Now I can say, okay, this one is more shiny. That's east or that's west coal, and it can send it. One, you're looking at it many different aspects. One, you're protecting the environment where you're not emitting so much emissions. You're not getting fined, and you're having the right mix versus panicking and then having a different mix, right? So, and even in mining, where you're mining copper or other material, you want to have a good camera that identifies the objects. So this kind of leads up to our project somewhat. If we were to make a product, as you guys said, you know, like, okay, scanning things, sports wise, or consumer use, credit cards. So if we were to make a product or we were to design a product, you're considering everything that's the frames, how it's going to process the data and take it out, and many applications, right? It doesn't have to be this exact camera with this family of product, but we have the right idea. We need an imager. We need something that's going to process the data, send it over, process it again, and then display it, or send it to something that's going to apply brakes or increase the speed or something else. Here we're looking at the frames synchronization, and this is to the deserializer to the GPIO, and here it's displaying. This is the GPIO looking at the data flow back and forth. And here the same thing, but a different application from the imager board to the serializer to the deserializer. Internal frames, looking at it, how it's coming in terms of the data, the frames. And again, we go back to the addresses, which are very critical when matching this up in terms of the hex addresses and writing the code and the data processing. Okay, hardware design, this is very critical for the electrical engineers. And this is, I must say, this is my area of expertise, or somewhat in this area the last 2 or 3 years. I got into it outside of work, and my work deals with part of it, the RF aspect of it. So confirm your I2C pull-ups for the serializer, the synchronization, confirm correct AC coupling caps, meaning these are your capacitors on the FPD link 3. So ensure that you have the right, you've selected the right capacitors, and when you select them, when you get them, also measure them. Ensure that you're measuring them and they are matching. They're matching to your value, because sometimes you could order something and you get it and it's out of spec. But if you don't measure it and you put it in, it's too late. You already have it on your board. Validate the capacitors, confirm the signal. And here you have the TDR, the time domain reflection, in terms of this whole system operates either on 100 ohm or 50 ohm. And if you have a cable before you use it on the system and you don't measure it, and that it's at, let's say, 38 ohms, and the system is working on 50 ohms, 9 out of 10 it will not work. And when I say 9 out of 10, the 10th is it will work, but it will give you an error message. Here, your return loss, transmission channel. This is all the connectors. This is the connections on this board. Matching from here to the serializer or to the deserializer, you match it 50 ohms, but once it leaves, it should be close to 50 ohms as possible, or 100 ohms. If it's not, you're going to have data that's not matched, because the internal filter into the hardware is set up such that it's looking for specific values. On your connectors here, it's looking for a specific value. So if that filter, if you have a value that goes outside of the filter spec, it's no longer recognizing it, and it's a data packet that has been missed. And the last thing, ensure proper POC. You want to take, whoever wants to take a wild guess of what this POC means, network design. So the coax cable, when we, HSD, okay. So the coax cable here, this is sending and receiving the data, the center contact right here, this center contact point right here, 50 ohms, center contact. Now going back to the camera, if we're using coax, right, one line coax, how do you think it's receiving its power? There's just one line between the serializer and deserializer. And as we look at this, the coax, this is for the data. Okay, almost there. Anybody, any wild guess? You can take a wild guess. Nope. I didn't know it, believe me, before starting on these projects 2 or 3 years back.
So is this the metal around this pin? I know that there are two shells, the pin in the middle, and then it's just like a wire, and then there is a metal shell around it, and isolation in between.
Close, you're very close. So this is power over coax. Because the camera is so small, and I'll go back here. So the coax connection is also providing the power too. You don't want to have two connectors, one for power, one for data. So you have, if you were running this over Ethernet, what they call poodle, power over data line, this is coax, this is power over coax. So within one system, you have the coaxial connection, you have the power on the shield, and then you have the data on the center contact. And I think I can show you that. Oops. Coax. Cross. Okay, yep, this is good. Or, yep, this is even better. So consider this, the center contact. This is where you have your data right here. Your data is flowing back and forth here, and the outer part of it here it's the shield contact, and the shield carries the power, and this is for your data. Yep, right here. This is good. This is a good observation of it. Your insulation is on the outside. What do you see? Your outer conductor, your dielectric, and then your center contact here. Center contact is solely responsible for the data here. This is the insulation or the dielectric material here, and the better the material here, the better for the channel performance. And then here you have your outer conductor, which is doing the power over coax here. If we were to look at this, power over coax. And then you have a filter here. The filter looks at it and says, okay, yes, I'm getting power, I'm sending it here, and then the data, I'm sending it here. So this is an expanded view of the camera system if you were to look at it mechanically. Again, the 953, this is only looking at the camera side. You have your lens here. You have your imager board. You have your serializer, and the connection goes from outside, from the coax onto the deserializer. Any questions regarding this?
The coax, it looks like very similar to the antenna one that we use for the TV in terms of the design aspects.
Yes, it could be. It could be. So consider this also, like mechanically, you have all of these parts, right?
Mm.
You have a lot of stack up and tolerancing, right?
Yeah.
You have 1, 2, 3, the housing, 4, the board, 5, 6, 7, and 8. So a lot to consider, right? I mean,
Right.
in terms of stack up, and it has to match evenly. And it's the same thing with programming. You're programming this board, you're programming this board, and onward, and then the receiver end. Here it comes down to pretty much this. That you have your power supply here, and then you have your I2C, CSI ports, and your clock. You're communicating from the imager to the serializer, and then onward to the deserializer. Serializer taking the image, deserialize, decode, decompress is to break down the image and then process it onward. And these cameras are not cheap. I mean, I'll show you here. This is $600, $650 with tax and shipping, right? And I think, in my view, the number of engineers we have here signed up already, 15, 3 or 4 of them software-wise, 3 electrical, mechanical, hardware, system level. This is just the students. And then the mentors also. I think you're fully capable of doing this. I actually have designed this camera system. I have designed one with TI and one with Maxim. So somewhat familiar with it. I started from scratch. It took me some time to get the basics of it, right? And then about 6-7 months later, I got it done. But with a team, I think you can do it much faster and much better. So here they go even in more details, where you have the 50 ohm here, 50 ohm, you ensure that it's matched. You want to make sure your capacitors are matched to coax or shielded twisted pair. And then here they go into the scripting. So in terms of looking at this, camera, if this is operating at 60 frames per second, you think it will be very cold or very hot camera?
So what do you mean by cold or hot? Is the temperature?
Yes, the temperature of the housing or the temperature of the camera. You think it will be?
Because it depends on the processing time. I mean, how much data you process. That's where you get the heat from.
Exactly, exactly.
So I had 400 frames per second. It used to be very hot, actually. So in terms of, if I look at it, compared it to 35, which is the regular camera, I don't feel the difference in temperature, but 60 probably gets a little bit higher temperature than the 35 that we regularly use for our webcams.
Exactly, exactly. So if we picked out, as you said, 400 frames per second, for the mechanical engineers, you guys have to make sure that this material doesn't trap the heat, right? It dissipates it, right? So consider that. Consider the material selection of this housing here. Is it going to be material that's going to trap the heat or dissipates it? It receives it on the inside and then it sends it out. Like it has a coefficient of, pretty good coefficient of dissipating the heat, 1. 2, software-wise, Ahmed, this question back to you. If the camera overheats, should you make a loop statement that maybe there's a temperature sensor here, a temperature sensor on the board, and if you think the board overheats, would you do that or should we do that? I think he's still with us. Ahmed, can you hear me? Okay, I think we might have lost them. Or any other software engineer that's on the line. Should we have a sensor here that's as Ghassan said, like if you're looking at 400 frames per second, it's going to get very hot, and you don't want to have a board that is going to start melting or have parts that's going to be not functional after you use it. So in terms of the software engineers or that are on the call, what would you do in this case? Or even not even the software engineers, but would you leave a sensor here that's constantly checking for a temperature if your frames per second, let's say, exceed 50? Because 50, as Ghassan said, and as I know, it doesn't get too hot. But if this camera is running 24 hours and it's running at 100 frames or 200 frames per second or 600 frames per second, would you put a sensor there for temperature?
I think, yeah, it would make sense because it would be exceeding, it would probably heat up, and it kind of just makes sense to put a sensor just to make sure no errors or nothing happens to the whole camera.
Yep, exactly. I mean, it's a safety precaution. You don't want to damage your hardware at the expense of something to keep running, right? If it gets to a certain temperature, just cut off. And you have multiple cameras. Let's say this was like a production Pepsi line, and you have 4 cameras. If this one got hot, it should go back to a controller that it's sensing the temperature is getting close to the maximum. The other camera should be turned on, and this one can shut off and cool down. Because these cameras, they don't come cheap, right? $600. This is 60 frames per second, right? Imagine a 400 frames per second. It's probably in the range of $4,000 to $5,000. Not cheap, and you don't want it to break down, right? Any other questions? I know we got into a little bit of the scripting here also. Each item here, like this is sensing, initializing the script for the sensor. It goes into it. This is port 1 on the 954, which is the deserializer. Go ahead, Ghassan.
So the question is, we have two types of cables that we use, the coax and the FPT. Is there a reason for that? Which one is transmitting better data or more accurate or capacity-wise? So you try to figure out which one is better for your application?
Yes, so you hit on a very important point in terms of the industrial application, right? Like if you're making 1 million of these and you look at it and you say, okay, I have less than 1 meter, but this is cleaner because this separates every pin. You don't need an extra filter. Coax, the cable is cheaper, right? When the cable is cheaper than shielded twisted pair, and you're making 1 million cars that use this camera, and then you're thinking about putting this camera on every car. Now every car needs these cameras, right? Every time you put in reverse, if you're an OEM, you need a rear view camera. If you're making a car after 2018, you have to have one of these. So if you're making 10 million cars, minimum 15 to 20, 15 or maximum 15 meters, let's say 12 meters of coax cable, that's a big saving, right? You know, like compared to this, let's say $1 a meter here versus $2.
Oh yeah,
Right.
so we're balancing the accuracy of the transmission with the price per
Yeah.
meter.
Yep.
Yeah, okay.
So as students, I don't want you to think about cost, but we shouldn't make it such that it's going to cost us a whole lot. But don't think about the cost, think about the functionality first. We can design two systems if that's the project we're going to pick in May. Could be a camera, could be a sensor, could be a high voltage module.
Okay.
But consider the cost, because ultimately, if this product that you see here, right? This product is going to make its way to the market, and it's going to be for 1,200, and this guy is selling it, D3 is selling it for 600. Who do you think the customers are going to go to? They're going to go to them, right?
Right.
So the same thing, like as you're designing as engineers, don't think about cost too much, but also consider that, because you don't want that to be the constraint as designers. But as you're working for a big company, a big organization, they'll probably come down and say, you know what, Ghassan or Ahmed or Mushtabah, we think you over-designed this. Now you have STP here, connector plus this, that's $3 over budget. And we're going to sell 10 million of these, that's 30 million. They're going to come back and challenge you to do it with coax because it's cheaper. But as far as engineering goes, we can do both systems. And I've done the coax. I'm sure I can do the STP with you guys. You know, as soon as we meet in person, we will dissect this whole camera with a board from TI like this, and then we will review each and every component of these. And then, you know, so like mechanical engineers, think about this board right here. And this is the deserializer. You see this board? All you have to do is walk on carpet or have a sweater on and the heat is on. And guess what? If you touch this board without touching the ground pads, what happens if you're touching the micro? You just sent all of the electric static discharge, ESD, all into this micro. You've blown it probably 9 out of 10. You've taken this out. So mechanically, we want to access these switches, this one, these switches, this connection, the power, these, but the rest of them, should you make a housing that leaves this part open? Probably not. You know, where we need access, we'll leave it open, but the housing that should be designed as such that does not allow the user to make a mistake and take out this whole board because they had ESD and they touched this micro. And the same thing here when you're designing the camera, mechanically looking at it, you want to ensure that everything is stacked up good. And they probably have this in a metal housing, I would say, because it can dissipate the heat, one, and two, as you touch it, it's already grounded. It's referenced back to ground, the housing. So with that being said,
I have a question.
go ahead.
So would it make sense to make the, if you go back to the block diagram, Buzz, would it make sense to have the communication?
I lost you after you said car communication.
Link. Would it make sense? Yep. Would it make sense if it's a wireless from like cost perspective? Or maybe it's a stupid question. I would like to decide.
No, you said it perfectly. Car cross section. I've been asked this question many times, Mo. You're not the first and you're not the last. So look at the body of the car, right? And look at it at the body of the car here. So most of the time, you see, where's the antenna? Right where my mouse is, right? It's open to the air, right? But
Yep.
imagine if your camera was in the back of the car here and it communicated to the head unit wirelessly. Once you have a frame of metal, plastic is okay. Different plastic, you have to check. But it would communicate from the back of the car to the front. Now, in a car, you cannot do it. In a house, you can, unless you had a house that is a metal, let's say you had cameras in front of the house. This can apply also for houses. If you had a camera here, here, and here, and here in the back, what do you think of the likely chance, this can go on to anybody, that the antenna can transmit through the metallic pieces? Probably not, cannot, right? Due to all the metal.
I have no idea.
Yeah, no, good question. But in the house, because the brick and the drywall, you can have a wireless camera outside of your house and it will transmit back to the gateway. And then it can say, oh, you know, there's somebody walking in front of the house, right? But if you had a metal frame behind the camera, it cannot transmit back to the house or block the RF signal, the wireless signal, the wireless signal from the camera to the gateway or the router that's taking the images. But if you have brick and you have a drywall, it will transmit right through it. Good question. The system can be done wirelessly in a house as long as the house is not metal, but cannot be done in a car because of all the metal structure that's in place.
Got it. Thanks.
Yep. So the last item I'm going to talk about, I'm going to say Ford Careers FPD link 3. I should have gone to LinkedIn, but it's okay. We'll do it this way. Link in. So I want to say Ford Motor Company or FPD link 3. And I'm going to say jobs. So the system we talked about is FPD Link 3. There's 2 suppliers. There's Maxim, GMSL, Gigabit Multimedia Serial Link, and there's FPD Link 3, 2 companies. They're very similar, but not the same. I just put in FPD Link 3, and it's in high demand. Like, if you know how to design the system, software, hardware-wise, mechanically. Vermeer, ADAS module, right? We go back to the meeting invite, and the first thing we had here was we talked about the ADAS module, right? The camera. TOF, time of flight, LiDAR, and other sensors. It takes you through the whole design. I wanted to go through it once with you guys, but you can go through it yourself. But the opportunities are limitless. FPD link 3, let's say GMSL, oops, GMSL 2. So there you go. I mean, like, this is Maxim, AMP Robotics. So this is a robotics company, has nothing to do with automotive, but they also use the automotive protocol. So in this mentorship, what we want to do is convey something that is of relevancy, right? We don't want to give you something that's not in the industry and that's not in high demand. I was contacted by Ford for a position regarding the FPD Link 3 camera for Ann Arbor. I'm probably not going to take it, but if you go through this and you design it, I think you can do pretty well, pretty good in the interview. And I will say, maybe if not this year, probably next year, we'll design a whole system. I know I have designed one. I can design 2 or 3 with you guys, either over shielded twisted pair or coax, have it go to a display or have it go to an ECU. But the demand is there. If you understand it electrically, just the basic, I mean, like here you can see the demand is, okay, C. So you can program this in C also, C, C++, Python, same thing here. But I would say most likely, they're going to ask you, how does this system function, right? And here, the PCB layout. Altium, we have licenses for this software. So when we meet in person, I'll give you guys access to the software. We'll create a username for each student, and then they're able to use it. So this is not only electrical, this is mechanical too. If you were to look at the PCB layout, the electrical engineer designs the PCB, but the mechanical engineer makes sure that the parts that are going onto the PCB, that stack up is done and done good. Because if electrically you have the pins there, but the part that comes there is like either too loose or it's hard to put on the board, and you solder it anyway, slight vibration, the solder joint will crack. And that will create a high resistance. and that will overheat over time. Any questions back to me in terms of what you guys thought about today's session? I like to welcome your feedback now, rather than presenting. Your feedback is greatly appreciated too.
Yeah, for me, it was a great session. I got a lot of information and new things. Since I started yesterday looking at the manual, watching the video, for me, a lot of abbreviation to learn. That's something extra. And also match some of the stuff that I already learned before with this new one to put it into perspective.
Great.
So great job. Thank you.
Somebody else? Or how can I improve this training? Maybe you wanted to see like the hardware setup or the hardware files.
Hey, Abbas.
Yes.
Yeah, I think this was a great session, in terms of laying out all these theories. For me, at least, it was very informative. And I think it would make much more sense when we apply it on an actual hardware where everybody on the call, mechanical engineer or electrical or software engineers, can really participate in making this, even if it's going to be like a very simple application. This would be, for the students, it would be very, very, helpful from adding on a resume perspective. For us, it also, for me at least, would be very, addition to my knowledge. That's all what I can comment on this. Applying it on an actual hardware would make it more informative, even more. But yeah, again, thanks. This was great.
Ibrahim? Maybe you're on mute, Ibrahim or Mushtaba?
Oh, hello.
Yes,
Sorry,
I can hear you.
Yeah, I thought the session was pretty helpful today, actually. I really liked it.
In your background is electrical, or if I recall?
So my background is mostly it's biomedical engineering, but I worked with like electrical systems and mechanical systems. I'm more so on the mechanical side, though.
Okay, so I'll give you an idea. Biomedical here, the camera system, you would use a laser rather than a camera, and you can apply this to treating specific cells in the human, right?
Yep.
And then biomedical engineering is you have a laser that's going to detect a specific cell and it's going to treat it or detect, identify.
Yeah, imaging is a huge part of the electrical side of biomedical engineering, with all that stuff like MRIs and things of that nature.
Great. Hadi or Mushtaba?
Yeah, no, I found the presentation really helpful. A lot of new things that I didn't know before that I'm learning along the way. Yeah, but I love the presentation, the way you portrayed everything, and thank you.
Yep, sounds good. Sounds good. So what I want to do is, like as I said earlier, we'll probably go through a different system, whether it's Coach or Captain Mo Mohammed from Ford. He'll talk about CAN. Suleimani from my friend from Europe. He's also like an expert in hardware. We'll probably have a software engineer. And as we get through these sessions, vaccine in place, the location opens, then we're able to sit down, think about a product, think about an idea, And then as we design it, we have all of these considerations, like, in terms of how do we want to come up with a camera system. We're not starting from zero. We already have something and we can build on it. And that's the objective that I have here, is pretty much to enable and empower you guys, for greater knowledge, and then open the door, in terms of the real world industrial applications. Mauricio, anything else back from you, or any feedback would be great if you have any.
Nah, for me it was cool, right? This is obviously I look at high voltage day in, day out, and then the high speed stuff I'm aware exists, but hearing it through like the proper terminology, the different protocols, and what can be done with it was good for me. Hopefully, after many of these sessions, we can pair it all together, or I can pair it all together in my mind and get a full picture.
Yep. Well, thank you guys. Enjoy your afternoon. For Mauricio, enjoy your morning. Hopefully it's sunny in California.
That's right.
Take care, guys.
Before you leave, Abbas, before you leave, first, good to hear your voice, Mauricio, back again. And for the rest, for the people who have engineering degrees right now and would like to have more opportunities applying for jobs, I was reached out last week, and I thought to mention it here in this meeting. Please feel free to contact me. You could have an opportunity with this my old staffing company, which I was hired at Ford. You guys might have a chance. So yep, feel free to do that. I think my email is. You can look up my emails in the chat, or
yes. Thank you, Mo, for the note. But what I'll do is I'll send out an email, and I'll include you in the CC, and then I will say, reach out to Hamad. Here's his email. Send him your CV to get in touch with the recruiter. But thank you for that note. I will, on top of this, I will send it out in an email. Reply back to everybody that's on the meeting invites. So, thank you, Mo. Yes, this is good. I'm a bit procrastinator when it comes to that stuff. I had the soccer practice earlier this morning, and I thought about a couple of times reaching out, but I forgot about it. Good thing you brought it up, and I will follow up in an email to all the students and engineers.
Thank you so much.
No worries. Thank you.
Yep, definitely.
Talk to you later, bye, guys.
Take care, guys. Enjoy your weekend. Bye-bye.
Thank you, same to you. Bye.